Welcome to the next lecture on synchronous machines course. In the previous class, we discussed regarding stator magnetic field and rotor magnetic field concepts in rotating electrical machines, including synchronous machines. And also we discussed what is the basic working condition, how AC voltage is induced in synchronous machine. Now, before proceeding to our next topic, let us try to solve a few example questions. Now, look at the question on your screen. A synchronous machine has its field winding on the stator. When running under steady state conditions, its air gap field is. 6 statements are given. Air gap field is stationary with respect to stator. Air gap field is rotating at a synchronous speed with respect to stator, rotating at synchronous speed in the direction of rotor rotation, rotating at ns with respect to rotor, rotating at ns with respect to rotor. Fourth, fifth statements are same. Okay, rotating in a direction opposite to rotor rotation. Now, what is the correct answer here is the question. See, it was clearly mentioned a synchronous machine has its field winding is on the stator, that means armature winding is on the rotor. Tell me one thing, field winding on stator, armature winding on rotor, that means is it like a DC machine? Because I told you in basic synchronous machine, armature winding will be on stator, field winding will be on rotor. But here it was clearly mentioned field winding is on stator, that means armature is on rotor. Rotating armature is nothing but a DC machine, because a DC machine and synchronous machine both are same. If I remove commutator and brush part of a DC machine, that is nothing but a synchronous machine only. So indirectly the given question is about working of a DC machine. Alright. Now tell me, in DC machine, air gap field we studied already. In DC machine, stator field stationary, right? Stator field stationary. Next point, rotor field is also stationary. Rotor field is also stationary. Therefore, air gap field is also stationary. No field is rotating. What about stator magnetic core? Stator is always stationary. But what about rotor? Rotor is not stationary. Rotor is rotating with a speed nr. This time nr is equal to ns. Okay, it was clearly mentioned rotor is rotating with a speed ns. Okay, now the first statement, its air gap field is stationary with respect to stator. You see, air gap field with respect to stator, both are stationary. Therefore, air gap field is stationary with respect to stator. That means first statement is correct. Second statement, air gap field rotating at synchronous speed with respect to stator. That is wrong. Air gap field with respect to stator, both are stationary, but the second statement they said synchronous speed. Therefore, second statement is wrong. Third statement, rotating at synchronous speed in the direction of rotor rotation, that is also wrong. It is not at all rotating. First of all, air gap field is stationary. Okay, next, rotating at ns with respect to rotor. Yes, that is correct. Rotating at ns with respect to rotor, because they are talking about air gap field with respect to rotor. Air gap field is stationary, rotor is rotating at a speed ns. Therefore, the relative speed will be definitely equal to ns, but it is rotating with respect to rotor. Exactly speaking, it is plus ns or minus ns, minus ns, but the question is only about magnitude. Therefore, ns can be correct. Next, fifth statement. I think fifth statement and fourth statement both are same. Okay, let me go to the sixth statement. Rotating in a direction opposite to rotor rotation, that is correct statement. Because as I told you, air gap field is stationary. It won't move. It is stationary. but rotor is rotating at a synchronous speed in clockwise direction, let us say. Therefore, what is the speed of air gap field with respect to rotor? Actually, speed of air gap field is 0. But with respect to rotor, if you see, it is said to be rotating in the direction of rotor or opposite direction of rotor. That example also I told you. You are moving on a bike, road is stationary. But with respect to your bike, the road is said to be moving in the direction of your bike or opposite direction? Opposite direction. That is what is mentioned in statement number 6. Therefore, sixth statement is correct. Fifth and fourth statements are same. I think it was a typing mistake. Anyway, so what are the correct statements here? 1, 4, 6 are the correct statements. Okay, it's a theoretical question. All right, let us try to solve one more question. Once again, a theoretical model. Look at the question on your screen. A synchronous machine has its field winding on rotor and polyphase armature winding on stator. When running under steady state conditions, its air gap field is. This time it was very clearly mentioned, field winding on rotor, armature winding on stator. That means, can I say it is the general synchronous machine? We know in general synchronous machine, magnetic field will be on rotor part of the machine and armature winding will be on stator part of the machine. Suppose if it is a DC machine, field will be on rotor, armature winding will be, field will be on stator, armature winding will be on rotor. But here clearly mentioned, field is on rotor, armature is on stator. This is definitely a synchronous machine concept. Okay. And we know in synchronous machine, stator field is rotating at how much speed? Synchronous speed. Rotor field is rotating at how much speed? Synchronous speed. Air gap field will also be rotating at synchronous speed. Okay, all fields are rotating at the same speed in the same direction. So relative speed is 0 among these three. What about stator magnetic core? Stator is always stationary. What about rotor magnetic core? Rotor is rotating, yes or not? At how much speed? Synchronous speed. Now look at the statements, and all the 5 statements are with respect to air gap field. Okay, so let me read the statements again. When running under steady state conditions, its air gap field is first statement, stationary with respect to stator. Air gap field is stationary with respect to stator. You see, air gap field with respect to stator. Air gap field is rotating with ns, stator is stationary, therefore can I say the relative speed is ns? But they said stationary, therefore first statement is wrong. Second statement, air gap field is rotating at synchronous speed with respect to stator. That is correct. Okay, the relative speed between air gap field and stator is ns. Second statement is correct. Third statement, air gap field is rotating at double the synchronous speed with respect to rotor. That is wrong. Air gap field, you see, air gap field with respect to rotor. You see, air gap field is ns, rotor is also ns, the relative speed is 0, but they said double the synchronous speed, therefore third statement is wrong. Fourth statement, air gap field is stationary with respect to rotor. Air gap field with respect to rotor. Air gap field is rotating at the ns, rotor is also rotating at ns, relative speed is 0. What is mean by relative speed is 0? Indirectly, air gap field is stationary with respect to rotor. Am I right or not? Therefore, fourth statement is also correct. Next, fifth statement, rotating at ns in the direction of rotor rotation. That is also correct. Air gap field is rotating at ns in the direction of rotor. There is a difference. Air gap field is rotating at ns in the direction of rotor or opposite direction of rotor? In the direction of rotor only. That is what they said in fifth statement. That is correct. Suppose if I modify that fifth statement like this, air gap field is rotating at ns with respect to rotor, then it would be a wrong statement. With respect to rotor means I have to take relative speed. Relative speed is 0. But they said in the fifth statement, air gap field is rotating in the direction of rotor or opposite direction of rotor, means the answer is in the direction of rotor. Okay. Therefore, what are the correct statements? 2, 4, 5 statements are correct. 1 and 3 are wrong. These kind of questions you will get as multiple select questions. Okay. Alright. Let us try to solve one more question. Look at the question on your screen. Two mechanically coupled alternators deliver power at 50 Hz and 60 Hz respectively. The highest speed of the alternators is how much? Okay, 4 options are given: 3600 RPM, 3000 RPM, 600 RPM, 500 RPM, like that. Okay, I am reading the question again. Two mechanically coupled alternators delivering their power at 50 Hz and 60 Hz respectively. Okay, then what is the highest speed of these alternators is? So question is very clear. There are two alternators. Let us say this is alternator number 1, this is alternator number 2. These two alternators are mechanically coupled. That was very clearly mentioned. Both are mechanically coupled means, can I say both will rotate at same speed? Obviously, yes. But alternator number 1 is delivering its power at 50 Hz frequency. Alternator number 2 is delivering power at 60 Hz frequency. Then what is the highest speed possible here is the question mark. Okay. So indirectly what you need to do is that you need to understand how many poles are required for these alternators. If you understand the number of poles, speed can be easily calculated. Because I know one thing, frequency is always equal to P into N by 120. As it is the first alternator, I can write it as F1 is equal to P1 into N by 120. I no need to write N1, N2, why? Because both machines are rotating at the same speed. So therefore, separate N value 120 into F1 by P1. This is the speed of the first machine. Similarly, F2 is equal to P2 into N by 120, where P2 is the number of poles in second machine. Separate N value 120 into F2 by P2. This is the speed of the second machine. But both speeds are same or different? Same, because both machines are mechanically coupled. So let me equate both of them. If I equate both of them, 120 F1 by P1 is equal to 120 F2 by P2. 120 will cancel. Therefore, P1 by P2 is equal to F1 by F2. Here, F1 means machine 1 operating frequency 50 Hz. F2 means 60 Hz. 0 will cancel. Therefore, P1 by P2 ratio should be equal to 5 by 6. Okay. That means the number of poles in first machine to number of poles in second machine should be in the ratio of 5 to 6. But if you understand the question, they are asking about highest speed possible. First of all, what is the speed equation? 120 F by P. They are asking about highest speed. Highest speed means, can I say number of poles should be the lowest value? So determine the possible poles combination, lowest poles combination, so that speed is the highest speed. But they should be in the range of 5 to 6 ratio. First, will you tell me, according to this ratio, that means if a second machine has 6 poles, first machine should have 5 poles. Is it possible for any machine to have 5 poles? No, because poles should be always even number. Therefore, 5 poles in first machine, 6 poles in second machine is not possible. If this is not a possible combination, then what you do is that simply multiply numerator with 2 and divide numerator with 2. Then what will be the ratio? Will become 10 by 12. That means first machine with 10 poles, second machine with 12 poles. Tell me, 10 poles and 12 poles are possible practically or not possible? Definitely possible. 10 is even number, 12 is also even number. Poles should be always even number. Therefore, the possible poles combination is 10 and 12. You may have a doubt, sir, why don't you multiply with 3 and divide with 3? Yes, you do that. If you multiply with 3 and divide with 3, you will get 15 and 18. 18 may be possible, but 15 is not possible. Then you multiply with 4. 5 into 4, 20, 6 into 4, 24. Yes, 20, 24 is possible. 20 is even number, 24 is also even number. But 20, 24 means more number of poles or less number of poles. You see, the poles number increases. When the poles number increases, speed will reduce. Okay, that means you will get a minimum speed, not maximum speed. But the answer required is, you see, once again, I need the highest possible speed. Highest possible speed means you need to select the minimum poles possibility. Minimum poles possibility. So therefore, what is the minimum poles possibility? 10 poles in first machine, 12 poles in second machine. 10 pole in first machine, 12 pole in second machine. If 10 poles are there in first machine, just substitute here. 120 into first machine is operating with how much frequency? 50 and 10 poles. Therefore, the possible speed is 600 rpm. 600 rpm is the highest possible speed, so that machine 1 can generate 50 Hz and machine 2 can generate 60 Hz. You will get the same answer even if you substitute here. 120 into what is the frequency at which the second machine is operating? 60 Hz divided by 12 poles, therefore 600 rpm. Okay. So the possible combination of poles are 10 poles in first machine, 12 poles in second machine. I would like to extend this example. Please try to answer the same question. Suppose two alternators are mechanically coupled. First alternator is generating 75 Hz frequency. Second alternator is generating 90 Hz frequency. Then what is the highest speed possible? Same procedure. Find out the suitable poles ratio and determine what is the highest speed possible. Highest speed means a minimum number of poles. Okay. That too, minimum doesn't mean 2 poles or 4 poles. It has to satisfy the ratio. Poles should satisfy this ratio and they should be minimum number. Okay. Then you will get the highest speed possible. Okay. Important model. This question repeated in almost all exams. GATE, ESE, PSUs, state services exams. Okay. Everywhere. Important model. Alright. Let us try to solve one more question. Look at the question on your screen. It is another analysis oriented question. Consider the following statements regarding the operation of a 3-phase synchronous machine given in the following figures. You see, there are 3 figures given, A, B and C. In every figure, if you understand, stator poles are mentioned, rotor poles are mentioned. Okay, and their direction of rotation is also given. Now, the statements here are machine A operating as motor, machine A operating as generator, B operating as motor, B operating as generator, C neither operating as motor nor operating as generator. So, what is the operating condition of each machine we need to decide here. Now, if you look at machine number 1, machine A here, these are stator poles. We know flux will always flow from north pole to south pole, or you remember one thing, north will always emit the flux. This is north, it will be emitting the flux. You see that this is how stator field is moving. Okay. Similarly, coming to the rotor if you see, inside the magnet flux will flow from south to north, outside the magnet flux will flow from north to south. Or you simply remember one point as I told you, north pole will always emit the flux. This is north pole, it will emit the flux like this. That means this is the direction of rotor field. Okay, and they are rotating in which direction? Arrow marks clearly mentioned in the problem, anti-clockwise direction. So can you tell me now, in the direction of rotation, which field is leading and which field is lagging? Yes, definitely rotor field is leading, stator field is lagging. That means it is a generating machine. We discussed already in the previous lecture. In case of generator, stator field will lead, rotor field will lag. Okay, therefore machine A is generator. Coming to machine B, once again, north pole will always emit the flux. This is north pole, it will be emitting the flux. That means this is the direction of stator field. Coming to the rotor, here you have north pole, it will emit the flux. This is the direction of rotor field. And they are rotating in which direction? Arrow marks are mentioned, anti-clockwise direction. Therefore, you tell me now, in the direction of rotation, which field is leading and which field is lagging? Yes, I can easily understand. In the direction of rotation, stator field is leading, rotor field is lagging. Therefore, it is a motoring machine. We know in motor, stator field will lead, rotor field will lag. Next, come to machine number C. Once again, stator two poles are there, north and south. North will emit the flux to the air gap. This is the direction of stator field. Okay. Coming to the rotor, rotor also has two poles, south and north, on the same line. North will always emit the flux. Therefore, you see this is rotor field. So, what is your understanding here? Stator field and rotor field are in phase with each other. So, if stator field and rotor field both are in phase with each other means the machine is neither a generator nor a motor. That is called as floating condition. Okay. In case of generator, rotor field will lead. In case of motor, stator field will lead. But here both are in phase. You can't define who is leading, who is lagging. Both are in phase. Therefore, machine is neither a generator nor a motor. Or also you can study in this manner as well. You remember the basic torque equation we developed. What is the basic torque equation? Torque is proportional to minus F1 F2 sine lambda. Here lambda is nothing but the angle between stator field and rotor field. Here both fields are in phase with each other. In phase with each other means what is the angle between the two? 0. You substitute that 0 degrees here, sine 0 is completely 0. If torque is equal to 0, then what about power? There is a relation between torque and power, right? What is the relation? Power is equal to torque into speed. If torque is equal to 0, power is also equal to 0. Power is 0 means machine is neither generating the power nor absorbing the power. That means machine is neither acting like generator nor acting like motor. It is under floating condition. We will call it as no load condition. If there is some load, some amount of power will exist, but there is no power, that means machine is under no load. It is neither acting like motor nor acting like generator. It is floating. Okay, right. So we will study in future what is exactly mean by floating and all, but right now this is the basic understanding. Okay, so machine is neither acting like a generator nor acting like a motor. So the correct answer is machine A generator, machine B motor, machine C neither a generator nor a motor. Or I can decide this may be a generator but there is no load. This may be a motor but there is no load. I can't decide. It may be a generator or may be a motor, but it is under no load condition. Okay, that is the correct answer. Alright, let us discuss about the next concept, that is construction of synchronous generator. Now coming to the construction part, based on the design of rotor circuit, synchronous generators are classified into two types. First one is salient pole synchronous generator. Second one, cylindrical rotor synchronous generator. I said these are the two types based on the construction of rotor magnetic circuit. Okay, whereas stator magnetic circuit is common between the two. Okay, whether it is a salient pole synchronous machine or cylindrical rotor synchronous machine, stator magnetic circuit will be same, only the rotor circuit design will be changed. Okay, so let us discuss about the first one, that is salient pole rotor synchronous generator. Second one is cylindrical rotor synchronous generator. These are the two types based on the rotor circuit, whereas stator design is same for both of them. Now let us first discuss about stator magnetic circuit, and then we will discuss independently about these two rotor magnetic circuits. Okay, now if you carefully examine the stator magnetic circuit design of a synchronous machine and induction machine, both are very similar. Why? Because In case of induction machine, stator magnetic circuit consists of three-phase balanced distributed winding. Even in case of a synchronous machine also, stator magnetic circuit consists of three-phase balanced distributed winding. So therefore, induction machine stator circuit I can use even for synchronous machine stators as well. Okay, let us discuss more in detail. Alright, the first observation here is stator is a circular cross section. You see the cross section looks like a circle and a cylindrical structured high permeability ferromagnetic material. The cross section may looks like a circle, but if you observe the overall shape, it will be like a cylindrical shaped high permeability ferromagnetic material. Okay, high permeability. What is the advantage if the permeability is high? If the permeability is very high, reluctance will become very low. Therefore, a small amount of magnetizing current will be sufficient to create more flux. Okay, high permeability ferromagnetic material. And the best example is silicon steel. Okay, so stator core will be designed using silicon steel material. We won't use CRGO steel. Grain oriented steel will not be used for circular magnetic cores like this. Grain oriented steel will be used only for transformer core, where the shape of the core will be axial in way. But here it is not axial, it is a circular core. So CRGO steel is not recommended. Non-oriented steel, that is silicon steel, will be used. What is the advantage of adding silicon? When silicon is added, eddy current losses will be slightly minimized. At the same time, as we are operating synchronous machine with AC supply, definitely the stator core must be laminated. Okay, because the supply frequency, if you consider an Indian supply frequency 50 Hz, so to minimize eddy current losses, stator core must be completely laminated. Next, the inner periphery of this stator magnetic circuit will be provided with number of slots. What is the purpose of a slot? The purpose of a slot is to place armature conductors. So these slots are generally used to place armature conductors. Okay, so every slot will be filled with armature conductors. Fine. All right. Okay, so and this is a distributed winding. And normally in majority of the cases, synchronous generators are always designed for three phases, because our normally existing power system is operating with three phase. So we will design synchronous generator also for three phases. When I said it is a three-phase armature circuit, we can connect this armature circuit either in star or in delta. Okay, so stator armature winding can be either a star or delta connection. Okay, so it can be either a star connection or a delta connection. Okay, most of the cases we will use star connection. Majority of synchronous machines are always star connected. Why star connection is majorly preferred? Because we know that for a given line voltage, the phase voltage is only 57.7% of line voltage. Therefore, the insulation requirement will reduce. That's why in majority of the cases, armature winding is star connected. By default, we will always assume star unless it is specifically given as delta. Okay, that is one more point. And we also know that slots are generally of three types: open slots, closed slots, semi-open slots. And synchronous machines are generally recommended to use semi-open slots. Okay, we will use semi-open slots because leakage flux is moderate value. At the same time, power factor is best. I discussed about the different types of slots in induction machine subject already. Okay, so we will use semi-open slots in most of the cases. Semi-open slots. Okay, that's all. These are the basic details regarding armature circuit or stator circuit of a synchronous machine. One more important point is that we always wanted to generate balanced voltages or unbalanced voltages? Balanced voltages. That means phase A, phase B, phase C, all three phases must generate same magnitude of voltage, but they should have 120 degrees phase angle difference. To generate same magnitude of voltage, every phase should have same number of slots. Suppose if overall 30 slots are available, then phase A 10 slots, phase B 10 slots, phase C 10 slots. Okay, therefore all phases are having the same number of slots, therefore we can expect same voltage will be generated. Suppose you select 40 slots in the entire stator part, then you tell me how many slots will come under each phase. Definitely 13 slots for one phase, 13 slots for one phase, but 14 slots for another phase. Okay, because of this what happens, the number of slots in each phase are not equal, therefore there is a chance of unbalanced voltages out of the machine. That's why the total number of slots what we are using in the stator part of synchronous machine, it must be always divisible by 3. Okay, slots must be always divisible by 3. Divisible by 3. All right, divisible by 3. So that means 30 slots by 3, 10, that is an integer number. 40 slots by 3, that is not an integer number. Therefore, all three phases may not generate same magnitude of voltage, that lead to unbalanced conditions. So that's why another important point during the construction of the machine is number of slots must be always divisible by 3. Therefore, all phases will have equal number of slots. Therefore, balanced voltages can be generated. Suppose if it is a two-phase machine, definitely number of slots must be divisible by 2. If it is a 6-phase machine, number of slots must be divisible by 6. Okay, like that. But most of the cases we are talking about 3-phase machine, so slots must be divisible by 3. Okay, then only balanced voltages are possible. Otherwise, unbalanced conditions will come into picture. Okay, this is one more important point. Now, the next major point is that I told you the difference between synchronous machine and DC machine. In DC machine, armature is on the rotor part, field is on the stator part. Whereas in synchronous machine, armature is on the stator part, field is on the rotor part. So, what are the advantages if armature winding is on the stator part of the machine is our discussion here. Okay, let's see. Okay, let us understand what are the various advantages if armature winding is on stator rather than on rotor. The first advantage I am repeatedly saying, that is current collection becomes very easy. Okay, current collection is easy because if winding is rotating, when you are trying to collect current from a rotating part, definitely arcing problems will be there. But here, as winding is stationary, collecting the current is very easy. Okay. Next, second important advantage is reduced number of slip rings. Reduced number of slip rings. Okay. Whether you keep armature winding on stator or rotor, slip rings are must and should. Suppose if armature winding is on rotor, as armature winding is a 3-phase winding, you need 3 slip rings. Suppose if armature winding is on stator, who will be on rotor? Field winding will be on rotor. And we are exciting field winding with which supply? DC supply. And DC supply will have only 2 terminals, positive and negative. Therefore, the number of slip rings are only 2 now. If armature winding is on rotor, number of slip rings would have been 3. Okay, that's why if armature winding is on stator part, number of slip rings are reduced. Rather than 3, now you need only 2 slip rings. Understand? Okay, that is another advantage. Next thing. Alright. The next point is stationary armature winding is mechanically very strong. We know as it is a rotating electrical machine, harmonics are always involved because flux will never be pure sinusoidal. I told you in induction machine as well. It will be a flat topped wave usually. That flat topped flux wave will have a number of harmonics in it. And those harmonics will create harmonic torques. And if armature winding is stationary, it can withstand all the mechanical forces created by the harmonics. Okay, that's why mechanically a stationary armature winding is very, very strong. Suppose if armature winding is on the rotor, these harmonic torques and certain centrifugal forces may make the armature winding very weak. Sometimes armature winding may come out of the slots and machine may damage also. That's why keeping armature winding on stator makes the winding mechanically very, very strong. Okay, this is another added advantage. One more important advantage of stationary armature winding is less amount of insulation. Okay, if you keep armature winding on the rotor part, definitely the amount of insulation requirement will increase. If you keep the same armature winding is on the stator, the amount of insulation requirement will reduce. Okay, experiment this theoretically we can't prove it, but when you construct the machine, practically you can understand the amount of insulation requirement will reduce. Okay, a practical analysis shows that if you consider a 500 megawatt alternator, if you keep armature winding is on the stator, the insulation requirement will reduce at least by 20%. That will save a lot of cost. Okay, so that is another advantage. Insulation requirement will reduce. Okay, another advantage of keeping armature winding on stator is cooling becomes very easy. We know that whenever you are operating any electrical machine, losses will generate. Because of that, the heat will rise, and in order to reduce that heat, we have to use coolants. Okay, the heat has to be dissipated, and that cooling system becomes very easy if armature winding is on the stator part rather than on the rotor part. Okay. Now another advantage of keeping armature winding on the stator part of the machine is the rotor weight will be reduced. We know that there are two windings in synchronous machine. One is armature winding, another one is field winding. But the power is mainly generated in which winding? Armature winding, from which the entire power will be collected from the machine. That's why the copper weight of armature winding is always very high compared to copper weight of field winding. Suppose if field winding copper weight is 10 kg, armature winding copper weight may be 100 kg or 120 kg. So such a large weight copper is now placed on the stator, and low weight copper winding, that is field winding, is on the rotor. That's why when you keep armature winding on the stator, the weight of rotor becomes very, very less. Tell me one thing, if weight is very less, can I say the rotor speed can be adjusted very easily? Suppose if there is a sudden load added on the machine, load means opposing torque. When there is a sudden opposition, the rotor speed will reduce. But as the rotor weight is very less, you can easily adjust the speed back to synchronous speed easily. Okay. Suppose if rotor weight is very high or very more, then getting back to the synchronous speed will take a lot of time, because weight is more, then inertia will be more. If inertia is more, rotor will take more time to get back to synchronous speed. But if the weight is very less, definitely rotor will take very less time in order to gain synchronous speed back. So the stability will increase whenever the rotor weight is reduced. So there are so many advantages like this. If you go on into the discussion, okay, micro level discussion, then you will find so many advantages. But these are the major advantages if you keep armature winding on the stator part of the alternator rather than rotor part. Can I say all these are going to be a disadvantage in DC machine? Even though these many disadvantages are there, we are still keeping armature winding on the rotor part of DC machine just to satisfy commutator and brush system. That is why these many disadvantages are there in DC machine. That's why DC machines are not recommended in practical use unless it is compulsory. Okay, unless it is compulsory. So most of the generating power plants are nowadays equipped with synchronous generators. Okay, so when armature winding is stationary, current collection is easy. Number of slip rings are reduced. Rather than 3, we need only 2 slip rings. Stationary armature winding is mechanically very strong. Less amount of insulation is sufficient. Cooling is very easy. Weight of rotor is less. So, when hunting phenomena takes place, the speed can gain back to synchronous speed very easily. So, stability will improve. So, these are all the advantages if armature winding is on the stator part. Okay. So, summary points about stator magnetic circuit is: Stator is a circular cross-section, cylindrical structured, high permeability ferromagnetic material. Usually silicon steel is used. And stator core is completely laminated in order to minimize eddy current losses. Inner periphery of stator is slotted to place armature conductors. And armature winding may be a star or may be a delta connection based on the voltage capacity. Okay. But to generate balanced voltages, slots divided by 3 should be always an integer, or you can say slots should be integer multiple of 3. Okay, that is another important point. Okay, and always semi-open slots are recommended. And these are the various advantages if armature winding is on the stator part of the machine.